Hello everyone, and welcome to another Leetcode video. Today we're looking at the problem Find Subtree Sizes After Changes, which is question 2 in the Biweekly contest 142. So this question reads that we're given a tree rooted at 0 that consists of n nodes numbered from 0 to n minus 1. The tree is represented by an array parent of size n, where each element in the array denotes what that node's parent is, and the edge case is that parent 0 has a parent of -1, since technically it is the root of the tree and has no parent. We're also given a string s of the same length, where it tells us that node, si, is assigned to that character. So node I belongs to character si. So we can make the following changes on the tree simultaneously for all the nodes. So what we're going to do is find the closest node to our node x that's an ancestor and has the same value. A little confusing, but we'll look at an example and see what this means. So if we don't find that node, then we just do nothing. Otherwise, what we want to do is basically assign that ancestor we found as a parent. So we remove the edge from x, our current node, and whatever its parent is, and we're going to make that ancestor node y the new parent of x. So after we make all these changes, what we want to do is we want to return an array of size n, where the answer of the ith element is the size of the tree rooted at that node I. So looking at the example -1, 0, 0, 1, 1, 1, and the string a, b, a, b, c, we'll see that our output is 6, 3, 1, 1, 1, 1. And this is because if you look at this diagram here, what will happen is that in this case, we would take this node 3 here, and we'd reassign its parent to 0. And why do we do this? Well, we see that 0 is an ancestor that has the same value. And notice we do not assign this 3 to node 2, because technically this is not an ancestor. We have to make sure that whatever node we're assigning to is actually some parent or ancestor of that current node. So once we make that change, we'd get a node tree rooted at 0 with size 6, a tree rooted at 1 with size 3, and so on and so forth. So basically what we're doing is we're going to reassign all these nodes, make the changes, and then return our answer at the end. So essentially in this problem, there are 2 steps that we have to take. So first, we have to actually make the changes to the tree based on the rules that were given. Then once we do that, we have to find the sizes of all of the subtrees. So remember, we have to do step 1 simultaneously, right? So we have to make sure that any change that we make does not affect any other changes that we need to make as we go through. So for example, if we decide to change a node here and assign a to 0, right, we have to make sure that when we find we do other nodes and process those nodes, we don't consider that change as part of the current tree, right? We want to make sure we're using the original tree. So how can we do this without actually having any conflicts? Well, you also notice that the way we're given this tree is kind of backwards of the way we usually work with trees, right? So say we're starting at node 0. We don't know which children to go to unless we look through every other node, right? We could potentially start at one of these and work our way back up to the root, but that's kind of backwards. So what we should do is rebuild this as a graph that's directed downward. So we could say we have our node 0, which will point to 1 and 2. We'll have our node 1, which points to 3, 4, and 5. And then that will essentially be our graph. We could also include these. So 2 points to nothing, 3 points to nothing, and then 5 points to nothing. But really, this gives us the entire layout of the tree that we need. So what we can do is we can use this to do our changes, right? And then what we can do is we can update this parent array as needed to reflect those changes, and then make sure that we don't have any conflicts, because we have what we're working with here, and then the actual state of the tree is going to be saved in our parent. So how do we actually do this? Well, we can now start at 0 and go down through the tree. While we do this, we want to keep track of the ancestors that we've seen. And remember, we are concerned with ancestors that have the same string value. So what we can do is anytime we see a string value, we can record where we saw that. So if we start at 0, we can say, I have an A at 0. Then we'll go down. We'll see, okay, I have a B at 1. So now I'll get to this 3. And what do I do here? Well, I see that I have an A in here already, and this is the closest ancestor. So what I want to do is say, well, I no longer have this connection here, right? I want to point this 3 up to this node. And how we do that is we say, I'm going to go to 0, 1, 2, 3, and I'll change this in my parent to 0. So you might think, okay, so now we're going to record this 3, right? And we could continue to go down if there are any other nodes here, but then when we come back up, what we want to do is we want to unrecord this, right? And why do we want to unrecord that 3? Well, basically, if we had, say, an A here, right, and we come back, we would still have that 3 in our hash map, right? So we want to make sure that when we're done processing a node, we revert back to any previous ancestors so that when we go back up the tree, we're not considering something we've seen potentially in another branch. So we're going to make sure that we undo any records that we do as we go down. So we're going to go back up. Now we'll go to 4. So here we see that technically we would want to make a change, but it's really a no-op because 1 is already our ancestor, and here it says to change it to 1 to really don't do anything here. So now we'd come down here. We could record this here, but we'd end up removing it. Nothing really to do with this node either. Then we work our way back up. And again, we'd come down to 2. We see that our ancestor here is 0. So we technically update it, but really it doesn't do anything for us. So then at the end, what we've done here is that we have now updated our tree so it's in the proper state that we want to use for our answer. But we have to update this graph as well to reflect those changes. So we can actually just rebuild this here. So what we would now say is that 0 points to 1, 2, and 3, and then 1 points to 4 and 5. So now we have this graph which represents the current state of our tree. So what do we actually do with this? Well, now again, we can just start at 0, and we can do a depth first search. So what we can do now is basically go starting from 0. And when we hit a leaf node, what we want to do is just return 1, right? So we'll return 1 here, return 1 here, return 1 here. And what we say here is that, well, the size of my tree is whatever the size of my subtrees are plus 1, and just return that back up. So once we actually update our tree, it's just a very simple depth first search, and we're going to record the size of all our trees in an answer array. So what's the time complexity here? So we're going to go through all of our end nodes once, right, to actually do the updates. We do the updates in constant time, so it doesn't really add time complexity onto us. And then we do another depth first search, which is another O of n, to actually get the sizes. So we have O of 2n here, but we simplify this down to just O of n, which would be our final time complexity. So let's hop over to the code and see exactly how this works. So the first thing we do is set up our graph here. What we're going to do is just going to start with an empty list for each element in the graph, and then iterate through all our parent array. And what we're doing here is just saying that if my parent is -1, this is a special case where we don't really have a parent, so we're just going to ignore it. And then otherwise, what we do is we're going to say this parent points to this child. So really, this graph is directed downwards starting at root 0. So here's the function where we're actually going to update our array. So first, what we're going to do is say if we have an ancestor, right, and that ancestor is not none, then what we want to do is we want to update whatever is in our parent node to point to that ancestor. And we do this because we know it's the closest parent that we have. And we know this because if we ever see a character, we're going to update its position. So for example, if we see an A at the root, but then further on down we see another A, we're going to update our A with that lower node that we found. So we know that we're always looking at the closest one. Here what we do is we want to keep track of the original value for this ancestor to make sure that we can revert back to it once we're done. So here what we say is that if there's no value in our ancestor right now, it means there's no ancestor in there, so we just default to none. Otherwise, we grab that value from our ancestors. Then what we do is we're going to record whatever node as an ancestor for future nodes. Then just do the DFS for all our children. Here is where we then revert back to our original ancestor to make sure that future nodes don't have an invalid ancestor value. So we call our function, and this will update our parent array for us. So now at this point, we have our parent array updated to reflect the proper tree that we want to work with. So here again, just kind of boilerplate, we're going to make a graph again, and we're also going to instantiate our answer array of size n. So then what we do is we're going to do another depth first search to just find the size. So first what we do is that we are going to check our edge case where we hit a leaf node. So basically what this says is that we're on a node and this node has no children. So in this case, we know that the tree is of size 1, so you can record this in our answer array and then also return 1. And we're returning 1 to tell our ancestors that our size is of 1. Then we say that the size of our current tree starts as 1 to represent our current node. Then we're just going to add to that whatever the size of our subtrees are. So we go through all of them, record their size, and add it to A. Then once we do all that, we're just going to record that value in our answer array and return that value for other nodes farther up. Then we just call that with our starting node of 0, and finally return our answer. So let's submit that and make sure that it works. And it does work. So hopefully this is helpful and it made sense. If you liked the video, please like and subscribe, and thank you for watching.